Welcome to Math 2318. This is section 6.7. We begin to look at inner product spaces. Inner product spaces are like the dot product. We have u dot v. You'll also see it written in this notation with the brackets. An interesting example, one that is infinite dimensional, is called a Hilbert space, or H2, and it has important implications in quantum mechanics. Just a side tip. All right, in question 2, we have an inner product, and the inner product between u and v is defined in terms of some action on their components. All right, so we have x and y, and they want us to make some calculations. So let's take a look. All right, so here's x, here's y. First off, they want us to calculate this. This is the magnitude of the vector, or its length. They write it with the two vertical bars so that you don't confuse it with absolute value. Well, the length is defined as the square root of their dot product. Well, so let's see, what is x dot x? All right, well, according to the formula, it's 2 times the first components plus 4 times the second, and so in this case, it's 22. So the length is the square root of 22. Similarly for y, using the definition of this particular inner product. Now, different inner products can have different formulas. So in this case, we're using the one they gave us. And so we've got 2 times 16 is 32, plus 4 is 36, and the square root of that is 6. All right, so those are the two lengths they asked us to find. What else did they ask us to find? They asked us to find, see, this is absolute value. So they want us to find x inner product with y, get that number. Take the absolute value and square it. All right, so let's see. What is x times y? So it's 2 times each of the components, 4 times each of the components, and so we get 24 minus 4 is 20. 20 squared, don't need the absolute value here, is 400. Now, they want us to find all the particular vectors that are orthogonal to y. What does that look like? Well, let's see. So using z as an arbitrary z that we're looking for, so z here, looks like z1 and z2. Okay. And so we're trying to figure out, well, what would this look like? What are all the vectors that are orthogonal or perpendicular to y? And they are perpendicular with respect to this inner product. Different inner products would have different things orthogonal. And so in this case, if you grind things out, you get that z1 has to be 1/2 z2, or they are of the form a constant multiple times 1, 2. So some beginning lookings at inner products. All right, in question 2, we have the space of second degree polynomials, and the inner product is defined as their evaluation at these points, -1, 0, and 1. So the way this works is two polynomials in P2. I'm going to have P at the first value times Q at the first value. And I do that for each of the values. So let's see, in our case, PQ would be P of -1, Q of -1, plus P of 0, Q of 0, plus P of 1, Q of 1. And so you simply take the particular P and Q, that were given to us and apply -1, 0, and 1. And when you grind through that calculation, you find that that inner product is 20. All right, in question 3, again, we have P2, that space of second degree polynomials. We have a different P and Q, and they want us to find the inner product. Same procedure, plug in the points for P and Q, so we've got that, and then add things up, and so you can see that the inner product can turn out to be a negative number. All right, in question 4, again, we are still in the space of second degree polynomials. It's going to be evaluated at -1, 0, and 1. So we want the orthogonal projection of Q. So we've got Q onto the space spanned by P. So we're going to project Q onto the subspace spanned by P, and it's done in an orthogonal way. So this projection is defined as the inner product of Q and P divided by the inner product of P and P, the thing we are spanning, and here's my spanning vector P. So really it's just a question of grinding this out. So I need QP, so they're evaluated at -1, 0, and 1. So just have to be careful as you plug in the values into P and Q. All right. So we get the first top part, which is 24. I repeat this for P and P. So we get 29. And so this is going to be 24 over 29. So there it is. Here's the vector P. And so multiplying this through, this gives me the orthogonal projection of Q onto the space spanned by the single vector P. All right, now in question 5, slightly different. We're evaluating at -2, -1, and 1. We're in the space P3. The items, the polynomials of degree 3. All right, and so we are forming the orthogonal projection onto the subspace. Now here, it's spanned by these two elements. All right, so here we have the projection. Since it's spanned by two elements, my projection is going to have pieces for each one. Okay, so as I'm looking at this problem and we're working it, I'm wondering why they picked P2 of t is t to the 6th power, since we should only have up to the 3rd power. So I think their mistake, but it will still work with the calculations here. All right, so let's see. So I'm going to have to plug these values in. So lots of things to grind out. So I need P0, P0, P1, P1, P2, P0, P2, P1. So I won't bore you with the details, but you have to plug it in to all three of your pieces and grind out that calculation. So just be careful. It's easy to lose a sign or miscalculate. All right, so when we finally get done, what we find out is this inner product was 130 over 4. P0 was just 1. P2, P1 is 0, which means that whole term is gone. And so the orthogonal projection is simply the constant 65 over 2. All right, and so then they asked us to, so we would like to find Q, which is orthogonal to P0 and P1. So here's my Q. All right, and so then Q at this value is a particular number, and they wanted us to scale it to get 1 minus 1 minus 1, 1. And when you do that scaling, it's simply multiply by 2 over 63. And when you simplify that, then you're done. All right, in question 6. So it seemed like a good idea when I assigned the problem, but it is long and tedious. So we're in P4, the polynomials of degree 4. And we're evaluating it at 1, 2, 3, 4, 5 places. Alright, so we're projecting it also onto the span of 3 vectors. So notice that when I do this projection, I've got 3 pieces to calculate, or 1, 2, 3, 4, 5, 6 inner products. And each of these 6 inner products has to be evaluated at our 5 places. So it's just long and tedious to grind out each one of these slowly. I'll let you follow it in the notes. There's no great details except be careful and don't lose a sign or a number. And so, when you finally get done being careful with all the bookkeeping and collecting information, what you find is this part falls away because the top is 0. This part falls away because the top is 0. P1 is 4t. Here's the number in the front. 4 goes into 160 40 times, and then take an 8 out of the top and the bottom and reduces to 17/5 t. So some interesting things with inner product spaces.